Okay, before getting to Verilog, let's have a quick review of digital fundamental. First, let's have the concept of combination logic and sequential logic. What is combination logic? It defines the output of logic cluster is only related to the current input value to that logic cluster. When the input value changes, the output value may change accordingly. For example, the logic gates we have learned in last parts, such as NAND and OR, exclusion OR, max, AND, and multiplier, are all combination logic cells. You can say using these cells you can get a combination logic cluster, or we can call it a combination logic. Let's take an AND gate for example. It has two inputs, in 0 and in 1, and with one output out. So when input changes, the output of this AND gate will toggle. While in this point, there is input change, but the output keeps the value of 0. So we say the output may change. So this is the same for all other gates. You can use many of these gates and click them up. They will be called as a combination logic. If you don't know the function of AND, OR, AND multiplier, you can go to part 1 of the whole class, simple theory and arithmetic data paths. I have introduced these functions in that part. So next, sequential logic. Its definition is the output of a logic cluster related to the current input value and previous status stored in sequential cells, such as DFF latch. The logic has the function of memory some information, such as the DFF. If there is no clock rising edge for this DFF, the Q output will not change. Even you change the value and to D input, the Q will keep stable, keep its last value. So it has the function of memory something in this cell. In a sequential circuit, you must have cells that can memory something. That is, you must have latch, DFF, or SRAM micro in that circuit. The cells that can memory data, we call them as sequential cells. Usually, these cells has an input pin of clock. The output will toggle at some event of the clock edge. For example, DFF will toggle at the rising edge of clock. So this is edge triggered, and this is level sensitive memory cell. Look at this logic cluster for example. It has DFF to memory something, and the output value will be related to the input, the value of this input, and some value stored in these DFFs. Also, it will related to this DFF. This output is almost the same. The output will rely on the value at here and the value of this DFF. And this output, the value will only related to the value of this DFF. This is also okay. So you can say for sequential circuit, there may be combination logic in it. Okay, sequential circuit may contain some combination logic, but combination logic can't contain any sequential cell. Okay, this is the basic concept of sequential logic and combination logic. and how they cooperate with each other, how sequential logic and combination logic are organized to form a function such as a counter or a CPU core. We will learn it in last section of this course. Okay. Logic values. This slide talks logic values in our digital circuit. Each bit is a 4-state value. It may in the status of 0, 1, Z, and X. So at a time, each bit may in either state of the 4. What is Z represent for and what is X represent for? This is a simple explain. Please note that X value is not allowed in the whole design. Usually this is not allowed, except at the power up time. After that, usually this X value is not allowed inside a circuit and in the I/O pad of a circuit. It may cause some problem. And Z value is only allowed at pads, that is input and output pads, the outer side of our chip. Why this is not allowed and why this is only allowed at pads is explained also in the first part of the whole course. Okay. And we also have deep explain for Z and X in the first part of this course. For an individual gate, if you give the X or Z value as the input, how it will respond to it and its output. So for inverter, if you give X or Z value, the output will always be X value. As it can't detect the input is 0 or 1, the output can be either 1 or either 0. So it output X value. And for AND gate, please see the two items first. One input is 0 and the other is X or Z, the output will be 0. This is because in the circuit level, in the view of CMOS gate. Okay, let's show you the logic gate. Okay, let's take the NAND gate for example. If you input at 0 is 0, so this will turn on. Okay, even if you have low or high Z value at this point, this CMOS gate will turn on and will drive the output to high value. Yes, this is the AND gate. So you have to add an inverter, and the output of the inverter must be 0. Okay, this is from the view of circuit of CMOS gate. Any value added with 0 will yield 0. But if one input is 1 and the other is X or Z, the output will be 0. Okay, you can't decide it's 1 or 0. So if you can't decide, the output will be denoted as X. And for OR gate, one input is 1, the output must be 1. Okay, no matter the other input is 0, X or Z. But input is 1 and the other input is X or Z, the output will be X. Okay, this is the table for exclusion OR gate. The fourth table shows how to resolve the output value of each gate if you give some input to X or Z. So if you see some Z value or X value in your simulation waveform, there must be some inputs some register B, X, or Z before it. Okay, let's see the binary encoding. You must be familiar with decimal encoding. That's what we use every day. That is, you have the number of 0 to 9 to express how big the number is. While in binary encoding, we just use the number 0 to 1. This is because in digital circuit, a bit only have two states, 1 or 0, or you can say two valid state. We just use the 1 or 0 two valid state to express the value of a number. So usually there are three encoding formats: the original code, this column, the original code. You just use the most significant bit as sign flag and the remaining bits as the amps value. So this is 0, 1 and -1. This is a sign flag. The remaining bits are amps value. So this is for 127 minus 127. Okay, this is the original code, and one's complement code, this column. One's complement is the same as original code for positive numbers, so they are the same. But for negative numbers, it will invert all the remaining bits. Okay, it will invert all the remaining bits. For example, this is -1. The sign bit is 1, and it will invert all the remaining bits in original code. Okay. And this last is 2's complement code. The positive number for 2's complement code is the same as original code. The difference for 2's complement is also at negative values. It will based on 1's complement and add 1 to it. So for -1, the encoding of 2's complement is first you get the 1's complement and add 1 to it, yields this value. And for -127, it's the same. You first get the 1's complement and add 1 to it, then yields this value. So for the first two coding, they have different codes for 0 and -0. For example, for the original code, you have -0. Actually, they are the same thing. And for 1's complement code, you have -0. But for 2's complement, there is low -0. For 8-bit representation, you can't express 128. Okay, the maximum positive number is 124. That is in this equation. This is the maximum number can be represented by a n-bit encoding. And for 2's complement, the minimum number can be represented is -128. That is in this equation. So this is a little strange, okay, a little unusual encoding. You need to take care of. And for the first two encoding, the minimum number is only -127. Okay, this is the minimum value for the first two encoding, and this is the minimum value for 2's complement encoding. So you can say for different coding mode, the value range may be different. And for the first two encoding, there is two different codes for the same value, 0. Okay, there is a question. In the computer system or digital circuit, the default encoding we choose is 2's complement 1. why we choose complement as the default coding format? Why not once complement or original code? This is we use. Why? Okay, you can think about it. The answer from me is consistency for the arithmetic operation. For example, if you want to do -2 and 3, okay, you can have a test. You can take out your pen and some papers and using this 3 encoding mode to calculate -2 and 3 and check whether the output is 1 in the same encoding format or not. Okay, this is called the consistency of arithmetic operation. And you need to notice the range. Okay, the value range of n bit to the complement code. The value range is minimum at this point, maximum at this point. And also we have hexadecimal format. This is simple. We just combine 4 bits of binary to a single character. Okay. So if you combine 4 bits of binary, it will in the value range of 0 to 15. And for value bigger than 10, we will use A to F to denote it. So for this binary, if you write it in hex format, it will be 21. Write it as 0x21. Okay. So for this in hex format is 8 line. For this is AF. Okay. Usually we combine from the LSB of binary. Okay. Combine this first, then count for the other 4 bits. Okay. Okay. Thanks.